In this lecture, we will discuss series solution method for nonlinear Volterra integral equation. In one of the lectures earlier, we saw the same series solution method for linear integral equation. The philosophy of this method changes for nonlinear integral equation. So suppose that the solution u of x can be written as an xn, and we know that the any function can be written in series form. So this is the series solution of u of x, or nonlinear Fredholm integral equation, I should say. So I need to change the topic and the nonlinear Fredholm integral equation. So we have nonlinear, non-homogeneous Fredholm integral equation over here, 0 to 1 kxt, and the nonlinearity comes from this function dt. What we do, we simply put equation 1 into equation number 2. So we have on the left hand side, we have n 0 to infinity a n xn. The problem here is there is a non-homogeneous function f of x. On the left hand side, we have a series of or polynomial in terms of x. If there could have been any, if there could have been any sign of x over here in f of x, then it would be difficult to compare the coefficients of x0, x raised to power 1, and so on. So what we will do, we will write a Taylor series of this function f of x. So we write it like this, Taylor series of f of x plus, and also suppose that we have lambda is equal to 1 for simplicity, 0 to 1 kxt, and there will be a function of u. So suppose that function is u of t. It is a function of u of t. So we replace this u of t with this series n 0 to infinity a n xn. I'm sorry, there should be tn dt. This is equation number 3. So we expand the series. On the left hand side, we can write a naught plus a1x plus a2x, so on, x square. On the right hand side, we have Taylor series of any non-homogeneous function. Then we have 0 to 1 kernel kxt, and we have a0 a1t plus a2t square, so on, dt. Okay, so that's how we treat the nonlinear integral equation. This is our equation number 4. So here we have discussed the theory of series solution method. It is a very simple method. You just need to put the value for u. We solve first example number 1. U of x is equal to 1 plus 7, 1, 2.59 divided by 7560 x 2309 divided by 2160 x square plus 1 by 36, and we have 0 to 1 x t square minus x square t u square t dt. So we put the equation 1, which is the series form of u of x. We put this on the left hand side. We get a naught plus a1x plus a2x square. On the right hand side, we have the same terms, will not change, plus 1 by 36, 1 by 36, 0 to 1, x t square minus x square t, and we put a naught plus a1t plus a2t square plus so on, and its square. Now the simple thing is we need to solve the, it is not as simple, I should say. We need to first take a second square of this series. You can take maybe a few terms over here. Maybe I just raise it. A naught plus a1t whole square. There will be infinite terms, but we cannot take square of infinite terms. On the left hand side, we have a naught plus a1 x plus a2x square. The right hand side, these terms remain the same, plus 1 by 36, 0 to 1, xt square minus x square t, and there is a square, a naught square, a1 square t square plus 2 a naught a1 t, and so on dt. So I think you can solve it yourself, and at the end you will get the coefficients. A naught, you will get one coefficient, might be 1. Then we have a1, you will get two coefficients, 1, 1.36 double triple one, something like that, and a2, 1, 1.4848 double three, and so on. All the other terms will be equal to 0. You just need to check that. After expanding, it will take time to multiply this with this term and then integrate it and compare with x raised to power 0 and x raised to power 1. There is a possibility that you will get two values for a naught. The exact solution is u of x is equal to 1 plus x square plus maybe plus, and all other terms are 0. And this will be one term. I'm sorry, this will be one term. We have taken this value a naught, a1, and a2. And then we have u of x for another value, which is 1 plus 1.36 x plus 1.484833 x square. All other terms are 0 as it is mentioned over here. So this was all about the series solution for nonlinear Volterra integral equation. Probably I will do maybe one more or example, but in the next video. So thank you for watching.